Observe a high-energy particle collision in a modern accelerator, and the sheer volume of raw data produced is staggering. To organize this data, we use a specialized vocabulary: velocity, momentum, force, and kinetic energy. But many of these concepts describe the same underlying properties in completely different ways. To process physical events mathematically, researchers must identify which of these values are independent and which are merely combinations of simpler, basic measurements. Beneath the thousands of specific equations used in physics lies a finite set of fundamental dimensions. These 7 units are the irreducible building blocks used to quantify every observable event in the universe. Scientists classify these as the SI base quantities. They form the minimum required vocabulary to describe the physical world. This system is represented by 7 distinct symbols: m, kg, s, a, k, mol, and cd. These dimensions are mutually independent. You cannot derive the meter from the kilogram, nor the second from the ampere. Because they are independent, every other metric or derived unit in physics is constructed by combining these 7 foundations in specific ratios. Viewing these units as independent axes, rather than a list of terms, provides a strict logical framework for understanding how physical laws are built. This framework begins with the domain of mechanics. The first foundational dimension is length, measured in meters, using the symbol m. Length provides the baseline for spatial dimensions, allowing us to quantify distance, area, and volume. The second dimension is mass, measured in kilograms, or kg. Mass quantifies inertia and the amount of physical substance present in a system, independent of its location. The third mechanical dimension is time, measured in seconds and denoted by the symbol s. The second dictates the progression of physical states, providing the interval needed to measure change. By combining just these 3 units, we can derive the formulas for velocity, acceleration, and force. Mastering length, mass, and time provides the complete mathematical vocabulary needed to model macro-level motion in classical physics. However, mechanics alone cannot quantify phenomena like electrical flow or light intensity. Describing these requires expanding into electromagnetism, thermodynamics, and optics. In our matrix, we add electric current, measured in amperes, or capital A. The ampere defines the fundamental rate at which electric charge flows through a point. For thermal physics, we use thermodynamic temperature, measured in Kelvin, or capital K. The Kelvin measures the absolute thermal energy of a system, a value that remains consistent regardless of the system's mass. The final units bridge the gap between microscopic particles and human perception. In chemistry, we track the amount of substance, measured in moles, or mol. The mole allows us to translate discrete atomic counts into a macroscopic scale that can be measured and manipulated in a laboratory. Finally, we add luminous intensity, measured in candelas, or CD. The candela is used to quantify the power of light as it is perceived by the human eye. With these 7 dimensions established, we have a complete universal alphabet capable of describing any physical state. While these 7 units are comprehensive, they face a challenge when applied across the extremes of the universe. Using a standard meter to measure both the diameter of a proton and the span of a galaxy results in numbers that are difficult to manage and communicate. Assigning entirely different units to each scale would require a constant series of arbitrary conversion factors, obscuring the direct relationship between large-scale and small-scale physics. The SI system solves this through the power of 10 scalar prefix system. This table maps prefixes like kilo, meta, micro, and nano to their specific exponential values. These prefixes are not new units. They function as modular mathematical multipliers. The system is symmetrical. A kilo multiplier of 10 to the third is mirrored by a millimultiplier of 10 to the negative third. This allows a single base dimension, like the meter, to scale across any magnitude while maintaining a consistent base 10 calculation. This consistent prefix matrix allows us to apply the exact same physical grammar to both quantum mechanics and astrophysics. By combining the 7 dimensions with the scalar matrix, we create a unified system of measurement. We apply a prefix to a base unit, such as kilo to the meter, to instantly create the kilometer. This shift changes the frame of reference for the observer while leaving the underlying base unit and its properties untouched. This allows for precise navigation across orders of magnitude, from the scale of planets to the scale of biological cells. Because the math is anchored in a base 10 system, physical laws remain calculable and consistent at every level of magnification. The complexity of the universe is distilled into just 7 dimensions and a modular scaling system. This system is more than a standard for measurement. It is a tool for verifying scientific theory. For any physical theory to be valid, the units involved must balance perfectly across every part of the equation. This logic provides the foundation for dimensional analysis, the practice of verifying the internal consistency of a physical formula. By stripping a complex formula down to its base symbols, kilograms, meters, and seconds, we can ensure that both sides of an equation are physically equivalent. If the dimensions do not match, the equation is flawed. This process allows physicists to mathematically prove the validity of a theoretical model before it is ever tested in a lab. With these 7 basis vectors and their scalar modifiers, the variety of the universe becomes a system that can be precisely measured, compared, and calculated.